We're going to talk about what are these conditions, what is the electrophile, for example, that we need to do this type of reaction, electrophilic aromatic substitution. So in the first place, we have an aromatic system. So we have this, say, benzene, and I want to install an electrophile there. So notice that, for example, when you had in the past studied alkenes, and let's draw just cyclohexene, I can do a bromination and say that I do that in carbon tetrachloride, and that will produce the dibromide that goes via ammonium intermediate and will produce this dibromide. That is the reaction. But if you do a benzene under the same experimental conditions, it will not react. So for that, in this system, we typically need a catalyst in a Lewis acid catalyst. So for benzene, the reaction is more stable and less reactive, say. So we're going to do bromination. In, for example, in the case of bromine, we can use iron and generate in situ what is a Lewis acid. The Lewis acid, in this case, will be that we're forming is iron tribromide. And we can also use aluminum tribromide, for example, and not chloride, bromide, because you need to use the same halide. Okay, so Lewis acid. What is a Lewis acid? Remember, these are species that electron deficient. For example, if you don't remember, borane, BH3 here, octet is incomplete. That is an example of a Lewis acid. So you generate the electrophile doing that, and then the substitution takes place via, as I explained in another video, now you form bromobenzene. So this reaction is very versatile, changing the electrophile. You can introduce a number of groups in the aromatic ring. So you can do, for example, you can synthesize chlorobenzene. In this case, you will need, as the electrophile, chlorine, say, and you use aluminum trichloride. You can do nitrobenzene. In that case, you use nitric acid, sulfuric acid. The way we generate the electrophiles, you should be looking at that in your textbook. How do you generate electrophiles? But typically, problems that you're solving is predicting products. So we're going to be looking at what is the electrophile. Here, the electrophile is NO2 plus, the nitronium. And you can also do a sulfonation. So benzene sulfonic acid is generated when you do benzene, you do the reaction with fuming sulfuric acid. Fuming sulfuric acid is sulfuric acid with SO3 gas. That is, we say fuming. So interesting. So there is a number of things that we can do. From benzene, you can also install alkyl groups and say that I put an arc here. And that when you do that, here, that is called Friedel Craft alkylation, other type of reaction. And that typically needs an alkyl halide and a Lewis acid. I'm going to put X instead of the halide. But there is a number of reactions that here we're going to be studying. One interesting reaction, though, in all of them, and that's different to the others, is the sulfonation. And why is that important to keep in mind? Other than all of the groups that we can start, we can do acylation and Friedel-Crafts. But what is the difference with sulfonation? When we have sulfonation reactions, if we have, say, that reaction is the only reaction that you're going to see here that is reversible. If you use fuming sulfuric acid, and again, that's with SO3 gas, you will install the sulfonic acid. In the forward direction, you do that fuming. But as you use sulfuric diluted or water, you will remove it. That's interesting because that means that we can install that group and do other chemistry in the molecule and then remove it. That's the most interesting use of that. So use it to protect a position. And it is so the reaction profile of the sulfonation reaction say that this is potential energy reaction coordinate. You're looking at something kind of like that. That once you form the sigma complex, it can go either way. So depending on the reaction conditions, you will have the sulfonated product, and let's draw it here, benzene sulfonic, or the reaction. That. Reversible. The other electrophilic aromatic substitution that we study, they have a different profile. If I use another electrophile, they will be sort of like that, lower here. So you will not have that reaction reversible. So that's the main use of that. So now we're going to be doing problems installing groups at the aromatic ring. One more thing we're going to need to study is how groups that already exist in the aromatic ring do orient the next substitution. We're going to see that later.